this is not the zero vector. Can this be written as another x squared? If the zero vector doesn't exist, then it's not worth your time going through the rest of it.
I've been teaching and tutoring math for over a quarter century, and I can help you get the results in less time.
Today, you're going to learn how to figure out if a subspace is indeed a vector space and how to properly define a subspace from a larger vector space. We're going to show you that with 3 different problems, and we're going to walk you through the important properties of a subspace as it relates to vector spaces.
Today on High Peak Education.
So let's go over what the definition of a vector space is and what the definition of a subspace is. So a vector space is mostly 2 things. It has these objects, and it's going to be closed under addition and closed under scalar multiplication. Those are the main 2 properties. In other words, if you add 2 vectors, add 2 objects, if you will, that are in the space, then the object that you get when you add those together is also in the space. And it's also closed under scalar multiplication. That is, a constant times that vector is also in the space. Now, these other properties where you can switch the order of adding vectors, where you can associate, where a zero vector also exists, you can add something to its opposite and get the zero vector, those all follow from being closed under addition. Closed under scalar multiplication means you can distribute a constant, or you can distribute constants over a single vector, or switch constants associating, and 1 times a vector is also in the space. Now, the idea is that when I say a vector is just an object in the space. It could be a real number, it could be a matrix, could be a vector, could be a tensor, some kind of math object. So that's going to be a vector space. Now, a subspace is just going to be a smaller part of a vector space. A subspace must be a vector space. So in other words, it also has to be closed under addition and closed under scalar multiplication. So it's a non-empty set, and it's a smaller part in general of the subspace capital V. And usually we call the subspace, if it's a subspace, capital W. So you have to have, again, these 2 main conditions. We're going to be seeing this a lot in today's video. So let's see if part A is a subspace or not. So we said that the vector space is the xy plane, and then the proposed W is a set of all points that are connected through the quadratic function of one term through the origin, a parabola through 0, 0. And then we just think of P is a real number constant. First of all, does the zero vector exist? So in other words, there has to be a point where all the parts of the thing are 0. If I had something like this, suppose I had matrices of the form A1, 0, B. That's not going to have the 0 vector, because even if I made A and B 0, this is not the 0 vector, because it's just got a 1. It's got a 1 there. I have to have everything 0 in your object, basically. So should we check closed under addition?
Can't you kind of already tell that it's going to be closed under multiplication? Because if you just multiply a scalar times another scalar, it'll just be a scalar.
It is going to check out under multiplication, because suppose we let Q be another constant, then you could say Q times Y would equal QPX squared. And then if you say let R equal PQ, then you would just have Y equal to RX squared, where R again is a real number. And then that'd be the case. So it is closed under scalar multiplication. But now let's check to see if it's closed under addition. To check if it's closed under addition, what we need to do is we need to choose 2 different x values. Let's go x1, x2, insert. So we're going to go y1 is px1 squared, y2 would be px2 squared. And we're going to try to add these bad boys. So the thing is, we hope it's still in the space if it is indeed a vector space, thus a subspace. When we add these together, we're going to have y1 plus y2. You can factor out the p. It's px1 squared plus x2 squared. But wait a minute, can this be written as another x squared? No. The only case that would be true is if this was like a Pythagorean triple, where the sum of 2 squares is also a square. So the question is the sum of two squares always a squared number? And the answer is going to be no. Because remember, if you want this to be having the properties of a vector space, this right here has to have the same structure as just like a regular input x squared. So W is not a vector space, so it is not a subspace of R2. Okay, thanks for checking out High Peak Education today. Would you do us a favor and like, subscribe, comment, and share this video? It really helps us to grow the channel, extend our reach, and it helps us to make more content like this to help you even more. Thanks for your support. Hope you're enjoying it. Let's get back to the video. Let's do the next one. Vector space, matrices, 2x2 matrices, but then W is the set of 2x2 matrices of this form. AB, 0, C, with A plus B equal to C, and A, B, and C all are real numbers. First question, does a zero vector exist? Yes, because if A equals B equals 0, then C equals 0, and you just have the zero matrix. So you have a zero object. So that's essentially your zero vector. So the zero vector exists. Then let's consider closed under addition. So when we do that, let's consider two different A's and two different B's. Especially given this right here, you think of A's and B's are basically the inputs and C is what results from A and B. So if I have this matrix, A1, B1, 0, then this entry would be A1 plus B1. Then we're going to check if it's closed under addition. So it's going to be A2, B2, 0, A2 plus B2. So let's add these together. So we're going to get A1 plus A2 in the upper left entry, B1 plus B2 in the upper right entry, 0. For reasons I think you'll see, let's go ahead and just reorder the addition. So it's A1 plus A2 plus B1 plus B2. But then I'm also going to propose grouping is a good idea sometimes, especially if you want to rebrand things. If I call this A3 in red and I call this B3, does this still follow the same pattern? In other words, do you still have A3 plus B3 in the lower right corner? Yeah, I think so, because this still has the same structure. A3 is there, B3 is there, and then A3 plus B3 is in the lower right corner. So they should all belong to the same group, the same type of vectors. So I'm going to suggest it is closed under addition. Let's see, last one, we got to do closed under scalar multiplication. Now, a lot of times we call that scalar C, but since we already have like A, B, and C, why don't we call the K? But then the question is, can K times the quantity of A plus B have the same structure as before? Again, think about rebranding things. Does it have the same pattern? So imagine when I highlight here, A4, then let me go ahead and highlight up here. So I'm going to call that B4. Then if I distribute this K into here, I think I would get KA plus KB. But wouldn't that just be A4 plus B4? Yeah. Do we still have the same structure that we were looking for? Yeah, because it has the same structure even though we did the scalar multiplication. So is it a vector space? It is a vector space. Therefore, W is a subspace of V. Last one. Vector space is C of negative infinity to infinity. W is the set of all negative functions of C between negative infinity and infinity. First of all, can we have the zero vector?
Would you not be able to have that because it's only the negative function?
Good job. All right. So the zero vector doesn't even exist. And remember, that's why I always recommend start off with the zero vector, because that's like the lowest hanging fruit. Because if the zero vector doesn't exist, then it's not worth your time going through the rest of it. So f of x equals 0 is not in the space of W. The zero vector does not exist, which means W is not a vector space. W is not a subspace of vector space V.